Modern AI models are hitting benchmark ceilings at an astonishing rate. We are pushing more parameters during training and millions of search loops during inference. Look at this chart. On the left, we see performance gains driven entirely by test time iteration, prompting and reflection cycles. On the right, we see an identical curve driven by training time scaling, actually updating the model's weights. Because these curves look exactly the same, the machine learning community often treats these two distinct mechanisms as interchangeable evidence of capability growth. But iteration is not Ascent. Extracting more performance from an existing model through repetitive loops is mathematically distinct from building a strictly stronger system. A high benchmark score proves an agent completed a task. It is structurally incapable of determining which underlying computational regime actually drove that success. Without a precise vocabulary to separate inference loops from true capability internalization, our models for forecasting AI progress are working from flawed data. To fix this, we need a theoretical language capable of defining the hard boundaries of an AI system's native potential. We find that language in historical computer science, classical oracle computability. In this framework, an oracle is a mathematical representation of the fixed capacity mechanically available to a deployed AI. It represents the strict limits set by a model's current weights and built-in rules. This framework maps AI development onto three rigorous computational regimes: within-layer activity, stabilized revision, and cross-layer ascent. The purpose of this framework is not to assign literal Turing degrees to language models. The goal is to classify structural boundaries. Classical computability definitively separates what a current model can do from what intrinsically requires a completely new model. This diagram establishes our baseline. This block represents a settled, deployed system, an AI operating under fixed update laws and architecture. We call this base oracle A. When you use chain-of-thought reflection, dynamic prompting, or fixed tool use loops, the system executes repetitive actions. Those actions operate entirely inside the settled system. Mathematically, this contained ecosystem is C of A. It encompasses all tasks that are Turing reducible to the base oracle A. Theorem 2 proves that finite internal self-modification is degree-bounded. No finite sequence of self-modification over a fixed layer can compute beyond it. In practice, providing a fixed model with an infinite inference budget or deeper search trees strictly restricts its output to C of A. Highly expressive search algorithms simulate open-ended learning, but if the update laws governing that search are fixed, the process cannot escape its base layer. Pacing slightly faster, more inference time compute is a deeper search of an already settled regime. Finite internal iteration structurally fails to realize true capability ascent. If we shift our focus from the finite process of looking and instead measure the converged output of an infinite correction process, we hit the canonical boundary. This is one-level stable revision, the theoretical state where iterative correction converges to a mathematically settled limit. Theorem 3, the relativized limit lemma, proves that if a stabilized outcome is limit computable relative to oracle A, it exists in a strictly harder computational class. We call this the jump-level regime, or A'. A converged, settled outcome belongs to this limit-governed class, rather than ordinary within-layer computation. Practical language models do not literally run chains of thought to infinite mathematical limits in production. But if an evaluation metric relies on the converged, stabilized output of a revision process, the researcher is no longer measuring the base model. They are measuring a mathematically distinct jump-level object. Crossing the capability boundary requires a structural change to the system itself. It requires an external guidance resource. That means human supervision, external reward signals, or novel search traces strictly outside the mathematical bounds of C of A. When post-training methods like distillation or reinforcement learning bake that previously external guidance directly into native weights, the system achieves capability internalization. This creates a successor system, Oracle B. This new regime natively performs what previously required external prompting and scaffolding. Proposition 3 mathematically proves that if a successor system capability internalizes a previously externally essential task, it occupies a strictly stronger relative level. System B dominates System A. True recursive improvement requires internalizing external reality to forge a computationally superior successor. We can apply these classical theorems directly to modern AI development. Consider a coding agent utilizing a fixed unit test verifier and search scaffolding. This diagnostic chart shows how we must classify the scores generated by this agent. We have one workflow, but three distinct mathematical readings. First, if the agent repeatedly calls the verifier under one already specified policy, this is finite composition. The task remains squarely in C of A. Second, if the evaluation metric extracts the final mathematically converged answer after exhaustive retries, the output sits in the jump level regime, A'. Third, if those exact search traces are used to distill a new checkpoint that writes the code natively without needing the verifier, external guidance is internalized. This is cross-layer ascent to Oracle B. A single empirical pipeline supports three distinct, mathematically incompatible realities, depending entirely on experimental design. Reporting a high benchmark score without explicitly defining which of these three paths produced it renders the data scientifically ambiguous. Leaving these computational boundaries unspecified introduces severe liabilities into AI research. In AI safety, treating heavily scaffolded, tool-reliant success as a model's native capability leads to systematically over-optimistic alignment evaluations. In capability forecasting, confusing inference scaling with actual successor stage growth distorts timelines for AGI development. When models are fed mathematically blurred data, predictions fail. Researchers must isolate their variables when claiming recursive improvement. Technical literature requires a rigorous taxonomy. A paper must explicitly delineate the base model's capacity from the fixed inference scaffold and separate both from genuinely internalized capability. Empirical smoothness on a chart is merely an observation of behavior. It does not erase the structural boundaries of intelligence.